Let's go ahead and get started. So, for the last two lectures, we've been investigating the geometric structure of space and time. And we've seen that there are many similarities between the structure of space and time in special relativity and the geometry of the Euclidean plane. And so today, I would like to make that a little bit more precise. And in doing so, I'll introduce a few more notions which will allow us to study the geometry of space and time. And in doing so, this will provide tools that we'll be using for the later parts of this course when we study other applications of special relativity. So let me just remind you of a few things that we have learned over the last week or so. So what we have seen is that although the spatial separation and time separation between a pair of events is something which is dependent on the observer who is measuring those spatial and time separations, the invariant interval delta S, defined by the equation that I have written here, is independent of the choice of observer, that is to say, independent of the coordinate system that is used in order to investigate, to measure those time and space separations. And in particular, if delta S is equal to 0, then that implies that those two events are connected by a light ray, in which case we say that they are null separated. If delta S is purely imaginary, which is to say that delta S squared is less than 0, then the events are time-like separated. And minus delta S squared over C squared is the square of what we call the proper time separating the two events. And that is the time between the two events as measured in the reference frame where they take place at the same location, i.e. as measured in the frame where the events are at rest. For example, if I have a clock which is moving at some velocity, then it would appear to you to be ticking more slowly than it would to an observer with respect to whom the clock is at rest. And the statement that the clock ticks once per second from the point of view of the clock's reference frame is the statement that the proper time between the ticks of the clock is 1 second, although the perceived time, the time that you might measure if you're moving at some relative velocity with respect to the clock, would not be equal to 1 second. And likewise, if delta S squared is positive, then we see that the events are space-like separated. And delta S is referred to as the proper distance between the events, which is to say the distance between the events as measured in the frame where the events are simultaneous. So if, for example, you have a meter stick, then in the frame where the meter stick is at rest, the distance between the endpoints is equal to 1 meter. So that is the statement that if you have a meter stick that is moving at some velocity, the proper distance between the endpoints of the meter stick is 1 meter, even though the apparent distance, as measured by you, a different observer, may be different from 1 meter. And using this, we explored notions of causality in special relativity. And we saw that 2 points that are space-like separated are causally disconnected or causally separated, and that no events which are causally separated can ever affect one another, provided the laws of physics respect the fact that nothing can travel faster than the speed of light. And for events that are time-like separated, it is possible for them to either to be causally connected, and in particular, if you have one event, which I've drawn with a little dot here, then those events which are in the causal future of that event are in the upper quadrant of this diagram, and those events which are in the causal past are in the lower quadrant of this diagram, where I am drawing a space-time diagram where the vertical axis is not time, but c times time, so that light rays travel on 45-degree lines. And on the left and right of these 45-degree lines, we have the regions which are space-like separated. And one can only define a invariant notion of whether an event happens before another or after another if those two events are time-like separated. If two events are space-like separated, there's no notion of which one happens first. Which one will happen first would depend on which observer is doing the observing. So, on these space-time diagrams, it's very useful to understand what the Lorentz transformations look like. And we saw that if, for example, we were to draw the XCT plane, and we were to draw the light cones, that is to say the 45-degree lines, which intersect the origin, then if you consider some other event, which is in the causal future, so it is time-like separated from the event at the origin, then if it takes place at the same point, it might lie exactly on the vertical axis of this diagram. But if you were to study the position and time at which this event took place in a different reference frame, then it would not appear to take place at precisely the same location x, but it might take place at some different location than the event at the origin. And what we know is that Lorentz transformations preserve the invariant interval, and the equation for the invariant interval, delta s squared, is delta x squared minus c delta t squared, is the equation for a hyperbola, which means that if you were to plot on this diagram the values of x and ct in some other coordinate system, so what we would normally call x and ct prime, then they would fall along the hyperbola defined by the curve of constant delta s. So, for example, in some other reference frame, some other observer might see the events as happening one at the origin and one at this other dot, which is not at the same location, but which is still in the future light cone. And likewise, if two events are space-like separated, then in one frame they might appear to be simultaneous, but in some other frame they will lie somewhere along that hyperboloid, which is found by solving for delta s squared equals to a constant. In order to make these diagrams a little clearer, and in order to understand the structure of these Lorentz transformations in a little bit more detail, it's also helpful to draw the x prime and t prime axes on the xt plane. So what do I mean when I say that? Well, this is the xt plane, and we would label events by drawing them as points on this xt plane. And what we would like to understand is how those labels will change, how the values of x and t would change if we measure those events in a different reference frame. So, what do I mean when I say a coordinate axis? Well, the x-axis I've drawn it here is just a horizontal line where t is equal to 0. And the t-axis is the vertical line where x is equal to 0. So that means that if I were to write down x prime, which according to our Lorentz transformation rule is x minus v times t, or I'll write that as v over c times ct, and set that equal to 0, then that defines the t prime axis. The t prime axis is the line defined by the equation that x prime is equal to 0. What does that line look like? Well, if you just look at the equation that I have drawn here, then it says that x is equal to v times t, if you said x prime equals to 0, or x is equal to v over c times ct, because I'm using the coordinate ct instead of t. And so that defines for me a line, which is not a vertical line, but rather a line with some slope. And so this is the t prime axis, or we could call it the ct prime axis. And likewise, setting t prime equals to 0. So what is that? T prime is t minus v over c squared times x equals to 0. Again, we could write this in terms of ct instead of t. So we would say we would just multiply both sides of this equation by c to say that ct prime is ct times v over c times x. That will define a line which is not horizontal, but rather differs from the horizontal x-axis by some angle. And it's easy enough to check, just using these equations, that the angle theta, that the x prime axis differs from the x-axis, and the t prime axis differs from the t-axis, is the same, and it's given by the equation tangent theta is equal to v over c. That's just the equation. That's just the statement that if you have the equation for a line, x equals v over c times t, then that differs from the vertical axis by an angle theta given by this equation. So you should compare this to the way that coordinate axes change under rotation. So if you have two coordinate axes, x and y, and then you rotate by an angle theta, then you would preserve the fact that there's a 90-degree angle between the x and y axes. And so they would rotate as in the manner that I've shown here. So x would go to x prime and y would go to y prime. But you see that special relativity does something slightly different. Instead, the coordinate axes get squashed a little bit. At least if v is positive, then the x and t axes will move closer and closer and closer to each other, as drawn on this diagram, as you increase the velocity. And as the velocity approaches the speed of light, v over c will approach 1, and theta will approach 45 degrees. So for a very large boost, which is to say for two frames that have a relative velocity that is very close to the speed of light, those two axes, x prime and t prime, will be very close to each other. Likewise, it should be easy for you to convince yourself that if the velocity is negative, actually what happens is you end up not having the x prime and t prime axes moving closer to each other in terms of the positive x and t quadrant, but rather that they do something like this. Okay. So we would have some angle there, theta, and some other angle there. So this is what the diagram for v positive, and this would be the diagram for v negative. And this would be the diagram of rotation here. And so you can immediately understand here, at least very roughly, how the x and t coordinates will change when you do a coordinate transformation. So let's say, for example, that we have an event taking place at a particular value of x and t, and then you go to some other frame in terms of the new axes x prime and ct prime, then in order to evaluate the x and t coordinates, you would project by drawing vertical and horizontal lines onto the x and t axes. Whereas if you wanted to compute the x prime, the values of x prime and t prime, you would project onto the x and t prime axes, not by using vertical lines, but by using lines that are bent with a relative angle theta with respect to vertical and horizontal. So you would project onto the x prime axis by drawing a line parallel to the t prime axis, and you would project onto the t prime axis by drawing an analogous line perpendicular to the x prime axis. And the values where those lines intersect these axes are the values of the x prime and t prime coordinates of that event. There was a question.
Yeah,
Yes.
What does the CF stand for?
Oh, CF is some Latin. Okay, CF is some Latin phrase. What does CF stand for? Does anyone know? It means compared to. C also. I don't actually know. It's some Latin phrase. Okay, your homework assignment is to look it up and explain it to me next time. It's some Latin phrase, right? It's like ETC stands for etc. And EG stands for example, except it's not example because there's a G and it's some weird Latin phrase. CF is some Latin phrase. Someone has their laptop here. You should look it up.
It's a compare.
Is that what it is?
Yeah, it means
Okay.
to bring it. Like,
Okay. There you go. What he said. Yeah. So compare it. Yeah. So you should compare in your mind those two things. Yes. It's always nice to inject a little Latin into our conversations. Yes.
so I'm noticing that if V is a C or a negative C, then the space and time axes are.
Yes. Yeah.
Yeah.
If you try, what does that mean? If you try and, so this is alluding to what I was saying earlier, which is that as V approaches C, these lines become closer and closer and closer to 45 degrees. What does this mean? This means that if you try and go to a frame where a beam of light is at rest, things become very confusing and the equations stop working. Okay, that's basically what it's saying. Yeah. And so at least this way of thinking about special relativity makes it very difficult to think about going to the rest frame of a photon. Question?
So when V equals C, so if they're exactly touching each other, you won't be able to connect the points.
Exactly. If the two, so yes, so another way of saying that is that if you take V equal to C, then the x prime and t prime axes coincide, and you're no longer able to label events by value, but you can't any longer label events on this space-time diagram by values of x prime and t prime. So what we would say is we would say that the coordinate system no longer makes sense. Good. We will always, in this class, at least consider boosts where V is less than C. Any other questions? Now, we have seen here that there is at least some very rough analogy between between the Euclidean formula Pythagorean's theorem, that the length between 2 points is the square root of x squared plus y squared, and the equation for the invariant interval. So now I would like to try and make that analogy a bit more precise and introduce you to a bit of the mathematics that we often use, which allows us to very easily study properties of Lorentz transformations. So first let me begin with a bit of sort of mysterious mumbo jumbo. Okay. So in Euclidean geometry, the length between 2 points is given by Pythagorean theorem, and this is the fundamental equation which defines the geometry of Euclidean space, i.e. the geometry studied by Euclid. the equation delta s squared is delta x squared minus c squared delta t squared defines what is known as the geometry of Minkowski space, i.e. the geometry studied by Minkowski. And Minkowski space is another name for space-time in special relativity. And the piece of mumbo-jumbo that I want to tell you is that these two formulas, the right-hand sides of these two formulas, become the same if I set y equals to I c times delta t. I, of course, being the square root of -1. So time is like an imaginary spatial direction. Okay. What do those words mean? Those words don't mean very much in and of themselves. But because of this analogy between those two equations, many of the formulas that you have learned in studying vector geometry, or you're studying Euclidean spaces, actually have very, very close analogies when studying Lorentzian geometry, that is to say, when studying special relativity. And in fact, the equation for the Lorentz transformation that we have written down in this class and derived using the postulates of special relativity is nothing more or nothing less than the usual equation for how vectors rotate in Euclidean geometry, provided one interprets one of the spatial directions as being imaginary. So let me now make that a little bit more precise. So, in order to do so, I either need to tell you or remind you of some statements about hyperbolic functions. Okay. There's a CD player which is continually ejecting this CD thing, and it keeps hitting my legs. So I'm just going to stand over here. Okay. So let me remind you. No, I'm serious. It keeps bumping into me. Okay. Let's remember a little bit of trigonometry. So, the trigonometry functions sine and cosine are fundamentally associated with the geometry of a circle. What do I mean by that? Well, consider the xy plane and imagine that you set x equals to cosine theta and y equals to sine theta, and then you increase theta starting at 0, where x is equal to 1 and y equals 0, and you increase theta all the way up to 2 pi. As you do that, the point that is mapped out on the xy plane is a circle. Okay, that's not a very good circle, but you know what a circle looks like. And in particular, the equation for the circle, x squared plus y squared equals 1, is just the equation that cosine squared theta plus sine squared theta is equal to 1. And here, let me redraw this circle a little bigger so I can draw on this picture. So if we want to understand exactly what the interpretation of that angle theta is, well, here's the angle theta. And in terms of the circle, theta is precisely the arc length that is swept out by this circle as you move from the point where theta equals 0 to the point where theta is given by some non-zero value. And so the coordinates of that point, again, are cosine theta and y is equal to sine theta. Okay. I would like to define analogous functions which are related not to the geometry of the unit circle, but to the geometry of the unit hyperboloid. So what is the unit hyperboloid? Well, the unit hyperboloid is given by the equation x squared minus t squared is equal to 1. Here, let me call this tau squared, where tau you should think of as c times t, because in the definition of hyperbolic functions, I don't necessarily want the speed of light popping around everywhere. So let me just consider a hyperboloid defined by the equation x squared minus tau squared is equal to 1. That will sweep out a hyperboloid that looks a little bit like this, which will asymptote to the axes with 45-degree lines. And I would like to define analogous functions, which will allow me to map out the points on this hyperboloid. Yes? Right now I'm thinking of hyperbola. Sorry. Hyperbola. Yeah. Sorry about that. No, I mean, if we were talking about higher dimensional relativity, of course we'd be talking about hyperboloid. Hyperbola. Good. Okay, so let's define some functions. Let me define the hyperbolic cosine of phi, otherwise known as cosh phi, as 1/2 e to the phi plus e to the minus phi. The hyperbolic sine, or sinh phi, is the difference between e to the phi and e to the minus phi. And just as the tangent is sine over cosine, the hyperbolic tangent, tanh, is sinh phi over cosh phi. And then you can check that the definition of these functions implies that cosh squared phi minus sinh squared phi is equal to 1. Just check it. It's easy. Just take the definitions, plug it in, and work it out. So what does that mean? That means if I start at a point, if I declare that I want to study points where x is given by cosh phi and tau is given by sinh phi, then as you start with phi is equal to 0, cosh phi will be equal to 1 and sinh phi is equal to 0. So you'll start at that point here, and then as you increase the value of phi, you'll map out points on this unit hyperboloid. And just as the angle theta was the arc length measured on the unit circle, this parameter phi is the arc length along the unit hyperbola. So if I were to draw graphs of these functions, cosh phi as a function of phi looks like this. That's not a very good graph. Sinh phi looks like this. And tanh phi is the ratio of those two functions. So at very large values of phi, both sinh and cosh look like e to the phi. So tanh phi approaches 1. And then it goes to 0 at phi is equal to 0, and approaches minus 1 at phi goes to minus infinity. Now, yes, question.
Cosh phi is 1 over
1 over 2? Sorry, is that not quite clear? It was 1/2. There's another question? No, you're just patting your head. It's okay. Now, unlike the unit circle, there's only one kind of unit circle where x squared plus y squared is equal to 1. There's two kinds of hyperbolas, right? There's one where x squared minus tau squared is equal to 1, and that's the one that I've drawn here. It's the one that's in the spatially separated quadrant, if I wanted to use the language of special relativity. But there's, of course, another hyperbola where x squared minus tau squared is equal to -1, which is given by a curve that looks like this, which asymptotes to be 45-degree lines. And there, it's given by the coordinates x equals sinh phi and tau equals cos phi. And analogously, I challenge you to write down the formula for the hyperboloid that lives on the negative tau side of the axis instead of the positive tau, as the one that I've drawn here. I'll give you a hint. You just put a minus sign in front of the cosh. It's not just a hint. That's the answer. It wasn't a very hard challenge. Okay. Are there any questions on this? I assume that if you haven't seen hyperbolic functions, then you're capable of going to the Wikipedia page and learning all you want about them. They're very useful for describing all sorts of things in physics and math, and you should become friends with them, because you don't want to be their enemy. Okay. Yes, question?
Doesn't phi also have to do with some area, like when you do a sweep out?
Yeah, it also can be defined in terms of an area.
Yeah.
Yeah.
Which area is it?
I don't remember. Yeah, this is what the Wikipedia page is for. Right, just like theta can also be defined in terms of the angle of the slice of the piece of pie. The angle contained in it is what? It's 2 pi over theta, 2 pi theta, something like that, or theta over 2 pi. No, something like that. I don't remember. You can look it up or work it out. No, don't look it up. Don't look it up. Work it out. Good. Other questions? Okay, now for a piece of magic. Cosine of I theta is cos theta. And sine of I theta is I times sinh theta. Now, you're not usually used to considering trigonometry for imaginary angles, but in fact, the trigonometry of imaginary angles is precisely the hyperbolic geometry that we've been studying today, because of these two formulas. And there are a variety of ways of understanding these two formulas. The easiest proof of these formulas comes from the identity that e to the I theta is cosine theta plus I sine theta. If you haven't seen that identity, prove it. The easiest way to prove it is by using the Taylor series expansion for the left and the right-hand sides of this equation. This is one of the most remarkable equations in mathematics, and in particular, it allows us to understand the relationship between the geometry of Euclidean space and that of Minkowski space. So why do I say that? So the rotation, where we take the xy coordinate system and we consider a new coordinate system, let's call it the x prime and y prime coordinate system, that is related by a relative angle theta to the x and y coordinate system, is given by x is cosine theta x prime plus sine theta y prime, and y is minus sine theta x prime plus cosine theta y prime. Or, if I want to write that a little more succinctly, I could assemble x and y into a column vector and write this equation as an equation of matrix multiplication on a column vector. And then you would see that the column vector whose elements are x and y are related to the column vector whose elements are x prime and y prime by the multiplication by the matrix whose entries are cosine theta, sine theta, minus sine theta, and cosine theta. To check that, just perform that matrix multiplication, and you'll see that all I've done is I've rewritten these equations. Now, can we write Lorentz transformations in the same way? By the way, how many of you have seen this form of a rotation written as a matrix? Okay, good. Most of you. If you haven't, make friends with it. Okay, good. So, the Lorentz Boost takes x to gamma times x prime plus vt prime, and t is equal to gamma times t prime plus v over c squared x prime, where gamma, as usual, is 1 over the square root of 1 minus v squared over c squared. Okay. Let's start playing around with this. Did I forget a sign?
I think the sign should be reversed. The top right should have a minus.
Oh, I'm sorry. There's a minus sign somewhere. Yeah. Did I get minus? Did I get the signs opposite? Is that right? Is that why you guys are all looking at me with a funny expression on your face, or is it some other reason? Did I? Let's see. Yeah. No, that's right. Is that right? Yeah, that's right. Thank you. Yeah.
I think there's another mistake up at the top. I think it should be cosine theta equals cosh I theta, and sine theta equals sine I theta over I.
Okay. Does that preclude these expressions from being true? Okay. Yeah. I mean, it's easy enough to work out. Should we derive it? Let's derive it. You should never remember formulas. You should only derive them. Okay? So cosine theta is 1 over 2 times e to the I theta plus e to the minus I theta, otherwise known as 1 over 2, otherwise known as cosh I theta. So cosine of I theta is cosh of minus theta, which is cosh of theta. So we're both right. Good questions? Other questions? Okay. So if you were to play around with it long enough, you could surely figure it out yourselves. But you know I'm here. I'm a nice guy, so I'll give you a little help. So let's consider that quantity v over c. So v over c for a Lorentz transformation runs between minus 1 and 1. And we discovered a hyperbolic function up above that ran between minus 1 and 1. It was the hyperbolic tangent. So what happens if we define a parameter phi known as the rapidity? The word velocity was already taken, so they called it rapidity. Defined by the equation that tanh phi is v over c. So what does gamma look like in terms of tanh phi? So gamma is 1 over the square root of 1 minus v squared over c squared, which is 1 over the square root of 1 minus tanh phi, which is sinh squared phi over cosh squared phi. And then let's go ahead and multiply both sides, the numerator and denominator of this expression, by cosh phi. So you get cosh phi over the square root of cosh squared phi minus sinh squared phi. But cosh squared phi minus sinh squared phi is 1. So this is just cosh phi. So the Lorentz transformation says that x is equal to cosh phi times x prime plus vt prime, which is v over c times t prime, which is tanh phi times t prime, and tanh phi times cosh phi is sinh phi. By the definition of tanh. And likewise, CT prime is, well, what is that? That's gamma times, so CT is gamma times CT prime. So that's cosh phi times CT prime plus the x prime term, which just as above, what do you get? You get a V over C, which is tanh phi times cosh phi, so you get a sinh phi. And I've written the formula in this order to make it clear that I could also write this in matrix notation. Where I assemble T and X into a column vector. And you view the Lorentz transformation as taking the coordinates C and T prime, organized into a column vector, and multiplying them by this matrix made up of coshes and sinches. And it's traditional to, when writing the space-time coordinates as a column vector, to put the T on the top instead of on the bottom. That's just a piece of notation. There's no physics there. It's just notation. But it's notation that will become more useful when we start considering more than one dimension. So, the thing that you really want to keep in mind is the analogy between this expression and this expression. The Lorentz transformation is a rotation by an imaginary angle. So, and just as we call the xy plane Euclidean space, we call the xct plane Minkowski space. And sometimes even we use units where c is equal to 1 to make the analogy sharper. So what do I mean when I say units where c is equal to 1? Well, usually we measure lengths in meters and times in seconds, but there's no reason why I couldn't measure lengths in light seconds and time in seconds. And then the speed of light is 1 light second per second. Okay. That's what the speed of light is. So that in those units, the speed of light would be equal to 1. Or alternatively, you could measure distances in meters, and you could measure time in meters in the amount of time it takes the speed of light to go 1 meter, okay, which is about 3 nanoseconds or something like that. Questions? Yeah. Yes. Sorry, in this derivation here? Okay, good. So I skipped an intermediate step in this derivation. So you're looking at this formula here. So x is gamma x prime. Gamma is cosh phi. So that says x is cosh phi x prime. And then you have this term here. What is that? That's gamma v times t prime. Okay. Otherwise known as gamma times v over c times ct prime. And what is gamma? Gamma is cosh phi. What is v over c? V of c is tanh phi, otherwise known as sinh phi over cosh phi. The cosh phi in the denominator gets rid of the cosh phi in the numerator coming from gamma, and you're left with a sinh phi. Okay. So what we've discovered is that what we thought of as a very clever derivation of Lorentz transformations was in fact a rediscovery of rotations between vectors in Euclidean space, albeit with this funny bit of mumbo jumbo that we think of one of the times as imaginary. There's a question.
Does phi relation to s squared?
No. What is phi? Phi, when we phi is another name for, it's another way of thinking about velocity. So just as I say, when I say that I have two frames that differ by some relative velocity, I could just as well say that they differ by some rapidity. Okay. What is velocity? Velocity is some quantity with dimensions of length over time, which varies between minus c and c. And so mathematically, it might be more convenient to talk about something dimensionless. So I take v and I divide it by c. And tanh phi runs from minus infinity to infinity instead of from minus c to c, or from 1 to minus 1. So it's just some different way. I'm free. It's a free country. So I can talk about, instead of velocity, I could talk about rapidity. Okay. I could say that I throw this pen at you with a rapidity equal to 0.00001. Okay. That is, that's something that one could talk about. So, for example, I welcome you to check that when v is very small compared to the speed of light, phi is very close to v over c. You can check that by Taylor expanding the left-hand side of this equation. And something that you'll also check on the next problem set is that the rules of matrix multiplication, along with the hyperbolic version of the multiple angle theorem, is the velocity addition formula. Okay. You'll discover that next time. Other questions? There was another question?
Okay. So for the Euclidean rotation matrix,
yes,
the eigenvalues are a 1 and a negative 1.
Yes.
For the one in the Minkowski space, are they going to be I and negative I?
Yeah.
Seems like appropriate.
Yeah, I think that's probably right. No, the eigenvalues are 1 and minus 1. I think so. Yeah, that's what it looks like to me.
Okay.
Let's try they're 1 and 1, not 1 and minus 1.
Okay.
Other questions? I think. Check it.
Yeah, I'm trying.
Okay. So there's one or two more things that I want to discuss before we complete our discussion of the geometry of special relativity. So first of all, I've been talking about events only that take place in an x and t coordinate system. But for events that take place in 3 spatial dimensions, we usually label them by a 3-component vector, x, y, and z. And in this case, the invariant interval is just the square root of the length of the vector delta x squared minus c squared delta t squared. And just because that delta x squared, you take that vector, the vector delta x, you square it using the usual dot product, and that gives you the length squared between those 2 points as measured in usual Euclidean geometry. And so the invariant interval takes precisely the same form in terms of that length squared now, minus c squared t squared. And the physical interpretation of delta s is the same. So that, for example, if delta s is real, then the 2 events are space-like separated. If it's imaginary, the 2 events are time-like separated. And if it's 0, the 2 events can be connected by a light ray. And the Lorentz transformations in 3 spatial dimensions are now those transformations which leave delta S unchanged. So, for example, there are various sorts of boosts that one can perform. There is the boost in the x direction, where you make a change of coordinates associated with a new frame that's moving in the x direction with some velocity v. So, in that case, the relationship between the x and the x prime coordinates would be exactly as we have discussed, and the y and z coordinates would go along for the ride. But you could also perform a boost in the y direction, meaning that t and y would get all mixed up by a Lorentz transformation, but x and z would go along for the ride. Or you could do a boost in the z direction, or you could do a boost in some direction that is some combination of x, y, and z. But there are other sorts of transformations that leave this invariant interval unchanged. Namely, those transformations which don't do anything to the t-coordinate at all. You could rotate around the z-axis. What does that do? That mixes the x and y coordinates. Okay, that's the rotation matrix that we wrote down earlier. And then that leaves the delta x squared part of the invariant interval unchanged. And it doesn't do anything to t. T just goes along for the ride. Or you could rotate around another one of the coordinate axes, like rotating around the x-axis mixes y and z together. Rotating around the y-axis mixes x and z together. Or you could rotate around some other axis. Okay, that is not one of these coordinate axes. And so you can see that in this way of thinking about the Lorentz transformations, they contain both boosts and rotations, all treated on more or less the same footing. And the set of all boosts and rotations that leave the invariant interval unchanged are known as the Lorentz group. And we often give a name to the set of all such transformations. Now, this is just a bit of mathematical jargon that contains no physics in it, but it's a word that I'll throw out there so that you recognize it. If you see it later in your lives, you call it SO3, 1. Question? So, when I'm talking about transformations here, I'm talking, When I talk about transformations here, I was talking about those which leave the origin invariant. Okay. You could also consider translations, which do also include boosts and rotations, but we give a different name to that group. We call that the Poincaré group. And the geometry of space-time in special relativity is completely understood in terms of these boosts, rotations, and translations. So in this class, we're not going to be talking about the Lorentz group or the Poincaré group or anything like that in any sophisticated way, but I want to throw those terms out there so that the next time someone says the Lorentz group to you, you know that they're talking about boosts and rotations in Minkowski space. Question?
Is there a similar name to the Poincaré group?
Yeah, there's a similar name, but people don't use it very much. It's called ISO 3, 1. Exactly. So 3 here stands for the fact that there's 3 spatial directions. 1 stands for the fact that there's 1 time direction. If I were to talk about the Lorentz group for the 2-dimensional Minkowski space, just the xt plane that we've been talking about, That would be SO11. Okay, I'll see you guys on Monday. Yeah, if there's a question, you can ask me after.